Okay, good afternoon, everyone. Good afternoon, everyone. It's my pleasure to introduce Professor Christopher Brown, and thanks for attending today's meeting. So, it is PhD in University of Vermont and his bachelor's and master's too. Professor Brown is Professor of Mechanical Engineering at WPI. He's the founder of Surface Metrology Lab. Then he worked on the engineering surface at Lansing Swiss Federal Institute of Technology. He was a senior research engineer at Atlas Co-European Research Center, working on process and product innovations. He has collaborated around the world in measuring and analyzing dinosaur footprints, archaeological artifacts, in replicas, cutting tools, and many kinds of additive surface. Professor Brown has published over 150 papers on surface metrology, and today's topic will be discussing on SUS axiomatic design, manufacturing, and sports engineering. So, Professor, we're talking today on engineering designs with SUS axiom, and thank you.
Thank you very much. Well, it's nice to be here again, and first time I've given one of these lectures outside of our nice building Washburn shops, which is the oldest building continuously used for engineering education in the country. So now we're over here in one that's a little bit younger, with fantastic views, by the way. I don't know who decided that this was a good location for a classroom. I guess give people something to look at while the lecture's going on. So, anyway, so I'm going to talk about approach to design that you haven't had a class with me or Professor Towner. There's a couple other people, I guess. Professor Cottonmore mentions it occasionally, and I've heard a couple other people are now too. I started teaching it here over 30 years ago. It's been a little slow to catch on, but I think it's very powerful, and it's one of the most valuable things that. Yeah, so I'm glad to be able to share with you. This is kind of funny. You U.S. engineers States are familiar with design theories. How many people here can name a design theory besides the one that's up there?
Yeah.
What design theory?
No, there's the design for manufacturability. There's also tiers or treads, which is the Russian.
Good for you. Thanks. So, okay. So, but one of the interesting things, all right, if you go to project presentation day, so here's students that have paid $250,000 and spent 4 years of their lives learning. Professional is we learn how to do design. So scientists look at things as they are and ask why. Engineers dream of things that never were and ask why not. You say, so what design method did you use for your design? Design theories are stuff too. GE Aerospace and ask the engineers there. So what design method are you using? And how is it different from what you did in high school? I try not to think about that when I'm flying on the planes that are powered by GE engines. Oh my goodness. So I think this is kind of a weak spot in our education. The other weak spot is, so how many of you know, without reading it here, canon of ethics for engineers? Everybody here either is or wants to be an engineer, right? And did you think ethics was unimportant? So why don't you know it? Because we don't teach it. What happens is if you happen not to be looking at your cell phone when you're walking down the stairs going out of Washburn. It's right over the stairs there, but most people are looking at their cell phones. Not very safely descending the stairs. Their eyes on the cell phone. If you've been paying attention to this over the last 100 years, we would not have been able to ruin the climate on this planet because climate change is not particularly good for the safety, health, and welfare of the public. And we could not ruin the climate on this planet without a lot of people that went to engineering school. It's not easy to change the climate on a planet. You've got to burn up a lot of dead dinosaurs. That means you got to get them out of the ground, and you got to get some ways of doing it and make a bunch of people rich while you're burning the dinosaurs. Takes engineering, but not ethical engineering. All right. So axiomatic design. So it's Sue's axiomatic design. Now Sue, more on him at the end. So you may have heard of that. That's sort of the WPI of Eastern Mass. That was supposed to be funny. So this proposition was, well, maybe all you people think that's serious. Yeah, they're just a W. So this interesting premise, proposition that there are axioms that apply to design. Just like we've got axioms or laws, rules that apply to mechanics, thermodynamics, electricity and magnetism. Why not engineering design? So they went looking for these self-consistent axioms back in the 70s. With the support of the National Science Foundation, they had something like 17 candidates and narrowed them to 2, and these seem to be pretty good. Let's get right into it. So the thing that makes it axiomatic, a lot of people that take my course think about decomposition as being important. That's important. That's sort of like the free body diagram, you need to apply them. But so axiom 1, main. So you want a design solution that's adjustable and controllable. Right? When you step on the brakes, you want the car just to stop in a straight line and not turn one way or the other, right? You want the design to be adjustable and controllable. You want to avoid unintended consequences. That's supposed to symbolize control over there. Symbolize unintended consequences and push this domino over, and eventually it's going to fall off. And this results in modularity, which we often talk about being advantageous, so that we have components in the design that can be deployed. And it's often the lack of this that leads to delays and cost overruns. So we can use this when we look at all the different possible solutions to a design problem to eliminate some of the coupling, lack of independence. So that was the first axiom. Second one is information. So these are well suited for Massachusetts. Board of Independence started in Massachusetts, and this is also the information revolution happened here as well. So the idea here is to maximize the probability of success. Now, because you have to think of, if you think of this in terms of probability, it makes more sense. Lots of times think, well, more information should be good, shouldn't it? But the more information that you need in order to accomplish something, the greater the chances that you will forget something or misinterpret something, and you won't be able to accomplish that. I think we've all experienced this. We have a wonderful software program here on campus that experienced. It's called Workday or Work All Day or Work Day and Night. And nobody seems to be able to get this to work efficiently because the instructions just go on, and they have to send us updates every day. I think it fails actually. The probability of success is so low. Anyway, I don't know how they selected it, but seems to be like a Rube Goldberg. So some people go, well, that's obvious. I know when I started using this at Atlas Copco before I came here, because I was introduced to this as a grad student, and now Sue came to Vermont to give us a talk. And we said, well, that's just common sense. And he goes, so what are the other possibilities? Sense, common nonsense, uncommon nonsense. Yeah, maybe just common sense, it should be. But how many people ever use that doing design work systematically? Anyway, so the idea is that they started off with 17 possibilities. The idea is make it simple. Sometimes we talk about Occam's razor. Discipline separately. That you end up, we're on the border, on the frontier with philosophy a lot. So axioms, scientific laws, cannot be proven. They are something that we use that seem to apply to a wide variety of instances that can be used to solve a wide variety of problems, but you can't prove. Can't prove F equals MA. So the question is, can we find violations of it? And I would invite you to be thinking about that and say, oh no, here's a design that's much better that has coupling. And let's talk about it. Every time I've taught axiomatic design, I have delivered that challenge and we come up with some interesting discussions, but we've never found a violation. So what's the alternative? And lots of times, if you ask somebody, what design method did you use? The usual. And some variation on algorithmic design. First, we must define it. Then we'll do some research and we'll brainstorm and then we'll choose the best solution. There's no clue here how. Tell if we're doing a good job brainstorming. What are we researching? But build prototypes, test the prototypes, and then redesign and start again. So it's interesting that this design method here that you find it in the text, and this is the usual one, the one most used. Let's just think about it for a moment and make a literally going around in circles. So, subjectivity. When do you stop? How do we see if we're making progress? What's the selection criteria? How do I represent the solution? Do I just communicate the solution? Do I just hand somebody the CAD file and go, here you go, I'm done? So is redesigning avoidable? Design is important. There's companies that have follow the sun design teams. If you're trying to come out with the next version of a smartphone before mid-December, before the beginning of December, so people have it for the holidays, it's important to get this thing designed. Making and testing prototypes takes time. You can avoid some of it, that would be good. So anyway, so the theory is that Sue's designs axioms apply to all good designs. I would contend that, and this is sort of maybe my engineering perspective, but I think any problem can be cast as an engineering design problem. And so if Sue's axiomatic design is the best solution to design problems, it therefore is the best solution to the method, so the theory and the method. So top down, you start with a big problem and then once you get all the components, physical integration, and you build it. And then at every step in the decomposition, you're applying the axioms. So in some ways, this decomposition is similar to a free body diagram mechanics. And there's some other similarities I think we may touch on as we go along. So we've got algorithmic versus axiomatic. So algorithmic approach. Correct process yields good result. It's not horrible. Most things have been designed this way. Requires iteration, trial and error. Evaluation criteria are missing. No way of selecting the best solution. Axiomatic. All right, so provides the axioms, guarantees the best solution for a set of FRs. These are functional requirements. So when you do design thinking, we need design thinking. And so somebody said, what is design thinking? Well, thinking about design. I know, I speak English. Okay, but what is it? Same words. Design thinking is about putting function first and then looking for physical solutions. So when we think about the functions that a design needs to accomplish, and we get a set of those, then we can start looking for physical solutions. And if we don't have the functions well defined first, then we haven't stated the problem properly. Anyway, so best solution for a set of functional requirements. And it gives us the structure and process for applying the axioms. Okay. So adjustability, axiom 1. Let's take a closer look at axiom 1 for a moment. So design is about solving problems. That means we're going to change something. And things are always changing. The universe isn't in equilibrium. Functions need to be adjusted. And so if we think about change for a moment, why is differential calculus so important? Differential calculus is about change, describing change. dx or x dt. Anyway, it's about how one thing changes with respect to another. So in design, I'm trying to change something. So, and this is like one of our foundations. We go study calculus. We don't always understand why we're studying calculus, but we're studying change. All right, let's take a closer look at axiom 2. So probability of success, I said, was the thing to do. And so Nam-Su defines this mathematically as a log of 1 over the probability of success. That is the information. Shannon's information, Boltzmann's statistical thermodynamics. So entropy, statistical thermodynamics. So it's got some basis. The idea is to reduce uncertainty and complexity. So we're uncomfortable with uncertainty. We would like, when we open up our cell phone, to be certain that we're going to be able to check our email or connect with our friends. We would like to be, when we climb on the airplane in Logan, we would like to be certain that we're going to arrive in Paris safely, right? We don't like uncertainty in engineering solutions. So we would like to minimize possibilities of malfunction and the other variables. So robust design. Okay. Some people, when I start talking about axiomatic design, almost get emotional. Why? You can't have rules for design. You know, it's like an art. This is engineering design, not a knife fight. We can't have rules. So, and when I have a chance, I go to an art museum. And we've got a great one down the street. If you haven't been there, I highly recommend it. Fortunate to have such a great art museum. Anyway, but science. I would say a science is a discipline. Science is much easier to teach principles as opposed to a whole bunch of facts. Sciences are easier to learn. I can learn the principles and figure out how to apply them. I got it. So we're talking about a scientific discipline, right? There's a scientific method, but so philosophy or science. So there is sort of natural history, natural philosophy, and so before we had science, it was all kind of philosophy, and the idea was, as this guy points out here, you know, so philosophy is what we call it before it's solidified into a science. It's molten state. So Sue's axioms, I would suggest, solidify philosophy of design into a scientific discipline. And we can think about what Galileo, Newton, and Einstein did. Science of some relativity. So commonality. Let's look at what Newton was thinking. So the idea was that Newton had this, there is a compact nature of the universe. There are principles for mechanics. So Newton was kind of stuck for a little while. So he was isolating himself during the pandemic on his a couple of years, put together some data from all the planetary motion that other people had gathered and thought about. Yeah, but you know what? We can explain all the motions of the planet with some invisible force that takes across empty space and holds all the planets in their orbits. If you think about it from this perspective, in the 1600s, you think, what was that guy smoking? I mean, invisible force. Whoa. The way things fall on Earth and the way the little lights move around the sky at night. Just a few of them. Most of them go whoosh, rotates, and they go through the sky, but there are some that just happen to be right on an east-west axis that keep changing their positions and move around, wandering through the sky. And that's why they're called planets. That was, if I understand right, planet. So anyway, recognizing commonalities and across a wide range. And so what did you guys accomplish during the pandemic? On my side. So, commonality. What is the basis here for what was Nam Su thinking? And we'll see in a moment. Worked on, and these are buses that are used in Korea. Currently, are charging your battery while you're driving or at a bus stop. By putting coils in the road, projecting the energy over 20-centimeter gap while the vehicle is over them. Place all the cars on the planet with lithium batteries, we're in trouble because there's not enough lithium on the planet. Half the weight of the car, half the cost of the car, and doesn't last as long as the others. Smaller battery and charge it while we drive around, it'd be better off. So it's a neat thing. Anyway, to be able to come up with that. Recognizing commonalities in design solutions across a wide range. About that. Schematic design. Is this like solving mechanics problems without Newton, before Newton? I don't remember exactly what it was like to solve mechanics problems before Newton. I was very young at the time. This was a joke too. You have to keep explaining when I'm telling a joke. Okay, so to the faucet. Question. Time. Figure out what the customer needs. So when you go in to wash your hands, if you're the customer washing your hands, you would like water at the right temperature and the right flow rate. You need it a little bit warm so it dissolves the soap and the stuff right to your hands, and you want enough of it so you're not there for a long time or getting drenched because the water's splashing out of the sink. All right, so what's the design solution? So one design solution, and I'm sure we've all seen this, we have a hot water valve and a cold water valve. That a good design. So can we tell? So you're all at least studying engineering, right? Supposed to be into design. Somebody's taking attendance and you go, oh my God. Or are you into trying to learn something about your profession? And what do you have to do to be an engineer? How can we tell if that's a good design? That,
It's not good design.
and you just walked in here. How do you know? I guess it's better not to come to my lecture. You can do better if you just walk in the middle.
I took your action and design course.
Oh. Something bad.
I have not taken the course, and while there are certainly more efficacious ways of doing that, that is a way to fulfill.
So it can fulfill the function. But all right, so to find out if this is a good design, what would so adjust the temperature and adjust the flow rate. Right? So we said we wanted water at the right temperature, water at the right flow rate. So if we're thinking about the customer, what does the customer want? Temperature, flow rate. How do I adjust it? Okay, cold water valve and hot water valve. So when I'm going into an unknown sink and I gotta wash my hands, I sort of turn them both on a little bit, put my hands under, it's too hot. So I turn up the cold, whoa, flow rate's too hot. And eventually I get it, which isn't bad if I'm washing my hands. I mean, I might walk out, my pants soaked and somebody's gonna wonder, was that an inside job? But it's, if I'm making expensive product and I have to adjust the production line like that, that could be expensive and slow. And if I don't know how to adjust it, because there might be more than just two things I'm trying to adjust, I'm not even sure I'm going to converge on a solution. So if we take a look at how we could represent this, so adjust temperature and adjust flow rate. Change the temperature and I change the flow rate. The hot water valve, again, change the temperature and the flow rate. So I don't have independence. I cannot independently adjust temperature or flow rate. Two controls I got, change both. So that violates axiom 1. It's a fully, what we call a fully coupled solution. So a better way would be like these little levers here, where I've got colder and hotter, moving it laterally, and more or less moving it vertically. And so here, lateral movement, just adjust the temperature, vertical movement, just adjust the flow rate. I get a diagonal matrix, fully independent. So that was axiom 1. Axiom 2, suppose I needed to design a clamp, and I'm going to represent it symbolically like this. So I've got a lever here that I can stretch this spring to try to squeeze these two plates together. So we have lots of situations like the seats you're sitting in have some sort of adjustment where I might be able to lock it in or open it up. So, and I want a certain clamping force, F plus or minus something. Too big a force, I break something. Too little force, the plate slip. So there's lots of systems like this. Your hubcaps. You don't want so big a force that you can't get the hubcap off if you've got to change the tire, and you don't want so little force to remove it that it falls off when you hit a bump. Which you might find in Worcester if you look carefully. All right. So the design equation is F equals KX. So let's look at this graphic. We'll put the FR on the vertical axis, the VP on the horizontal. Force. There's my tolerance. Too much force, I break it. Too little force, it slips. So I've got a stiff spring and a soft spring that I can choose between. Which one do I axiom 2? The soft spring. I want a really quick response. I want to lock that thing in. But if you think about where temperature change, all kinds of things that can change the size of that cam surface that I was trying to represent on the previous slide. Tolerance I can get. Variation in manufacturing. I want a bigger tire. So I would like the softer spring. So whenever we have a linear system like that, like this, and be able to choose or the design problem. Faced with you're doing your MQB and you're thinking, well, let's see which component should I put in here? Which one's gonna work best? Figuring that. So longest is the best, variance, accommodates impact. Also, though, the soft spring takes up more room and more displacement. So maybe there's a constraint on how big it can be. So within the constraint, maybe I take the softest spring. So if I want to look at axiomatic design, hey, I can't see it from here. What were they thinking? So I cannot, so I can pretend I'm not looking at it. Okay. So trying to decompose axiomatic design so that people can kind of see. Hold it up. And so we get two kinds of decomposition that we'll go over in a moment. And then a process for building that structure. So the structure describes the design solution. And lots of times I'm using words to help define because design can be a noun or a verb. So the design solution is the result. This is what we're going for. The complete design solution. Okay, and the process. Zigzagging decomposition, physical integration. So design thinking, I forgot to put this slide in here. So design thinking has been known for a long time. Prior to Sullivan, though, a lot of the designs for buildings were neoclassical, big columns with all kinds of fancy stuff. So if you go to like most business schools that are into that, of course, WPI, our buildings are practical. Sort of. Washburn, the snow blows in through my window, it's going the right way, and it's rip. It stays there all day. I can keep my drinks cold. So summertime when it gets hotter than it's anyway. It's not like we got a functional building over there, but and it's almost older than Sullivan. But the idea was, let's think about what a building is for and design. And we're kind of used to this now, right? And we can recognize that sorry, this is sort of a contemporary building. It's not as old as WPI. So develop functions first. First the function, then the form. So the form we call design parameters. That confuses some people. That's what goes on the print or in the CAD file. So we can think about different domains that we work with in design. We already talked about the customer needs, the CN. Then there's the process domain. How do we make it? And that becomes very important if you're making some things that nobody's ever thought of before, like an integrated circuit back in the 1950s. Gazillion transistors in a very little space. And nobody's done that before, so there was a lot of process development. But usually you come around here, you go, oh, I can. Print it or something. So we don't often But often we can define problems just using FRs and DPs, and that's the way most of the literature looks at it. And we'll try to focus on that. So at the top, this is a top-down thing. So we looked at the horizontal. Now so the horizontal kind of lays out like this. We start with the CNs, and these can be almost any kind of format. But then we get some rules for the FRs. These have to be things we can design to. So it's necessary the customer needs to understand them. FRs are going to be things we can design to, and then the corresponding thing is the DP. So right at the top of the whole thing, we call it FR0 and DP0. And then we might have process variables, so just to remember they might be. So we're kind of narrowing the scope. So as we choose the physical solution that is going to best satisfy the FR or fulfill the FR, we're narrowing the scope. So we can decompose this. In other words, when we have a big problem to do, in other words, you can't I think I'll design a 787. And so you just start sketching with the wheels and you work up and you go, there's the whole thing. You're going to want some team to work on the landing gear, and they're even going to divide it up. And some team to work on the airframe, which for the 787 was pretty novel. And so you need to decompose them so that, and there's lots of things we have to decompose. If you're faced with eating a great big steak, or if you're a vegetarian, a big eggplant, you cannot fit it all in your mouth. You have to cut it up. And you got to put size chunks. So the idea here is you can decompose, it doesn't have to be into 3 and then 2 or something. It can be any number. When I got to work with Nam Su on a project to design the crew survivability system for the next orbital space plane, which former President George W. canceled on us, but we had spent a lot of time on that, and we had over 2,000 FRDP pairs. Anyway, so the idea is here I can keep decomposing. And for some reason they call it, I'm going to decompose it down to the leaf level. I get down, the leaves are up, but anyway, nuts and bolts, to where the solution's obvious. We get it down some level where we can figure it out. Abstract to detail. Often as engineers, we like the details, and we're jumping in down at the detailed level before we really figured out what the whole. So anyways, here's sort of a summary. We've got horizontal domains, we have vertical and hierarchies and detail. And we've got children at each level. And so these are children detailing FR1, this would be 1.1, so forth. And we do zigzagging, first the function, then the physical part, function, physical, and keep cost, satisfying the customer needs. So here's another way of looking at it. So different structures, and then decompose. So and then we got to figure out how to put it all together physically. So when we're decomposing like a car, we might worry about the brake system in a functional way, but then when we go to integrate it physically, somehow we have to make sure that the driver can step on the brakes that are actually going to squeeze the disc at the wheels. So the physical integration may be different than the functional processes. Most of the work that has been done theoretically is done on the decomposition. Anyway, but they're applied, the axioms are applied to both. And so, like I said, you can think about this as similar to the free body diagram. And if you want, so in a free body diagram, fx, fy, fz, Cartesians, they're all orthogonal. So I can change fx without changing fy or fz because they are orthogonal. So when I think about independence, axiom 1, I want to be able to change fr1 without messing up fr2. So I want something that's orthogonal. I want them independent. So what we're doing is we're taking our design problem and defining it in a multidimensional orthogonal space. So when we're thinking about physical space, 3 dimensions seems to be enough, and we get sort of troubled by trying. But mathematically, it's not hard. We just keep saying, all right, it's orthogonal. So multi-dimensional orthogonal spaces. We're defining our design that way. Orthogonal means it's independent. So if we look at this like from set theory, suppose it so that the children add to the parent. So it's collectively exhaustive. We haven't missed anything in the decomp. Suppose that we get all of the components that made up the parent. And so we can sum the children somehow to equal the parent. That means some sort of summation, not necessarily linear, going to add to the parent, exactly. And some people go, so collectively exhaustive means I thought of everything. Remember one student said to me, well, you never think of everything. You better, you're the engineer. When you forget something, people get hurt. It's your responsibility. So you need some theme for decomposing. And decompose so that you don't miss things. So decomposition rules. Those rule. All right. So FR start with verbs are stated in the imperative. For those of English class where they actually. So we want the minimum number of FRs. And the sort of the mnemonic here, if you like, mnemonic is C min. It's a good thing to think about while you're doing decomposition equations. We have children somehow combining people with parent. And the design equations, and the design equations show how the DPs set apart. We can represent it vectorially, and we've had a little look at this. So we get a design matrix, which we already saw in the case of the faucet, and we use linear algebra and square because we need 1 DP for each FR. If you've got 1 DP trying to satisfy more than 1 FR, you can't adjust them independently. But if you end up with a situation like that in your design, you should say, do I really need those FRs as being independent? Do I need to adjust those independently? So you can do linear algebra, don't get too scared, because you don't need to be real good at linear algebra. This is not to influence the FR. So we can represent the design matrix simply this way by just looking at all of the coefficients that change it. And so you can set it up and then represent it. So just like with the faucet, we would like the off diagonal terms to be 0 so we can adjust each FR independently with each DP in any order that we like. But if we can't do that, this is at least adjustable in a triangular form. And you know, from linear algebra, I can rearrange this so that I can get lots of things into a triangular form that maybe weren't. But once it's in a triangular form, there's only one order of adjustment. Because when I adjust DP1 to get FR1 where I want it, the rest can go out of adjustment, but six. I finally get FR6 for it. So that is adjustable. There's an interesting thing that Nam points out in his 3rd book, which I'll show you in a moment. We're just about done. A thing called imaginary complexity. So we look at this matrix and say, uh-oh, this is operations to adjust it, if in fact I can figure out some strategy so that it converges. And Nam calls this imaginary complexity. So we can rearrange it using linear algebra rules, preserve the equalities in the equations, and then set it up this way. So 1, 2, 3 is not a good order of adjustment, because when I do that, you can see I get things out of adjustment, but 2 will do it. So so that way I get the matrix into a triangular form. And so there are systems that you can look at which appear to be unadjustable. You know, God, it's a pain because I have to keep iterating to get this. But if you can figure out what the relations are between the physical solutions and the functions on the components that you're trying to adjust, it may just be imaginary complexity. Anyway, metrics. This one just quickly as we're getting up. Sometimes, especially when we're doing design, don't like to have to deal with metrics. But if we can't measure it, we can't improve it. And there's some things that we also, we'll do design reviews. And how do we measure the progress of design and design reviews? Well, axiomatic design gives us a way to do that. We measure creativity and innovation. Anyway, so a key here is decomposition. We look at how our design is progressing by how the decomposition is progressing. Equations and axiomatic design, and so this is sort of fulfilling the need to have metrics. So I don't know how my animations get so mixed up, but so Nam ended up doing 4 books on axiomatic design, and from publishing standpoint, it's an interesting thing. Got frustrated, actually. He also has a book called Physics, which is about topology, friction lubrication, where it's upsetting the status quo. And to axiomatic design, he was submitting his papers, and his papers were getting axioms for design. Who does he think he is? God? And so one of the editors was my was looking at reviews that he got back from one of Nam's papers for the journal he was editor of, and he goes, "This is crazy. Nam doesn't write bad papers. How come these guys don't like the paper? I don't get it." So as editor, he read the paper, which the editor doesn't always get to do. Usually they accept the reviewers, and he started thinking about the 2 axioms, and he said, I went around and for a couple of days and thought about it, and every design thing I could look at, he's right. And so he published it under his authority as the editor. But now I'm getting sick of these negative reviews and just said, I'll write a book. The last one just came out. Minor role in that. But, anyway. So Nam was a president of KAIST, the Korean Advanced Institute for Science and Technology, which is quite an amazing place if you get a chance to visit it. It's online electric vehicle. So here's an example of a car. And Nam got his group to professors to work on axiomatic design. The EE professors to run a vehicle over 20 centimeters, that won't work. And decompose it, decompose it, decompose it, until the solutions are obvious. Yes, there are some things that won't work, but if you do a good decomposition, you can find solutions that may not be evident before you decompose it. Funny story, the president of Korea came to visit to see how it's going, and Nam wanted to give him a ride in the online electric vehicle, and security detail for the president So you can't drive around in the car. Now, can you just sit in it? So the president got in. Now I'm sat in the driver's seat, president sat in the passenger seat. They closed the doors and the security detail was chasing them on foot. He was pretty sure of his position. He was pretty sure the security detail wasn't going to be able to fire him. But anyway, so that's something about the way that works. You have the coils that create an electric field. The coils in the vehicle. Korea has a west coast, so sandy and sloping, and an east coast that's open to the Sea of Japan. And the idea would be that you don't need harbors, which are rather destructive to the environment. Wetlands and things are important. So this is a system where you can unload cargo ships at sea with all the pitch and roll, put the container hovercraft, so you don't need to modify the shoreline very much, and just run the hovercraft up to a railhead. Everywhere. You could design ships that were just for crossing the ocean and not for docking, so you could leave off like side thrusters. Anyway. So Nam is was NSF engineering director and the department head at IT, president of KAIST, and he got his first honorary doctorate here at WPI. Working with one of our alums and trustees, Walter. Probably in all the shoe soles that we're wearing right now. To expand the polyurethanes. I don't have time for questions. You can always take my class. That's a good wrong answer, though. Whole paramount corporate profits. So I suggested, why don't you put the first canon of and then they were wondering about what to do on the entrance. Old paramount corporate profits. And that was the last time that guy spoke to me. He was so upset. If it's not, what is it? Since Reagan, the most important thing for corporations, stockholder value. Stockholder value. That came in with Reagan. I don't see a desperate signal from Professor Powell that we have to.
Slides are available on Canvas as mentioned. I'll tell you all about it, more than I can. But, way of understanding design.
You're welcome.
All right.
Thanks for coming, everybody.
Okay.
Yeah, look at a couple of different things.
Now to start.